עינת לא ברורה בתשובות שלה.
כן, לא, נראה לי היא כוונה עד סוף הרצאה 5. שזה בעצם כולל את החישוב של פונקציית הקורלציה.
קניתי את זה מכיר את החנות היפנית הזאת, הדון דון דונקי?
לא.
חנות מטורפת, קניתי את זה שם, אבל לא הסכימו לי להעביר את זה בשדה, שמע איזה בלאגן.
באמת? תשמע, זה היה כוחר קצת.
כן, אבל אתה יודע, אני פותח להם, אני אומר, תקשיבו, זה מטריה, אומרים לי לא, זה חרב.
אז מה בסוף זה? בסוף
עשיתי להם בלאגן, אמרו לי, טוב, לך לכבודה החריגה, תשלח את זה ככבודה חריגה. שלחתי ככבודה חריגה.
איזה הזויה?
כן. זה אחד הדברים הכי דפוקים שקרו לי.
Hello. So the quiz will start at 6 after the lecture. And now we will continue a little bit the treatment of the correlations and the fluctuations that we started last week. I remind you that the correlation function that we developed had a very specific structure. So we had the correlation function. And the correlation function has a structure, G of R, the correlation of fluctuations. Okay, so the assumption is there is some sort of a uniform solution which is described by mean field, on top of which we introduce fluctuations. We look on the correlations of those correlations of the fluctuations, and we obtain that it behaves as, well, c to 3 minus d divided by 2, r1 minus d divided by 2, and exponent minus r divided by c. Okay. And c is the correlation length. C approximately as 1 over square root of t minus tc. What we see over here is the following. First of all, there are domains of correlated fields. Right? The size of this domain is described by C, the correlation length, because when you go far away or far away from a specific region, which is described by the size of Xi, there are absolutely no correlations due to the exponential decay, and you don't care. Right? So the fluctuations do not speak to each other, the fields are completely uncorrelated, and you can assume that you only have the mean field solution. That's the assumption. The problem over here is, first of all, is that the correlation length itself, okay, so the sizes of those domains of correlated fluctuations, is diverging as you approach the critical point. Okay? So something funky happens over there, and what we started to do is to answer two questions. First of all, are those correlations ruining the order, right? Because if indeed, first of all, at least in the limit when the correlation lengths go to infinity, think about it. I have fluctuations of this type over here, fluctuations of those type is over there, another fluctuation and more fluctuation, more fluctuations. So maybe all those fluctuations completely, okay, completely destroy the order that is described by the Ginzburg-Landau criteria. Right? So we obtain that there is an ordered state. Somehow, well, build your Ginzburg-Landau Hamiltonian, obtain the ordered states using the saddle point approximation. Great. But there are fluctuations. Do those fluctuations destroy the order? Yes or no? This is number one. Number two, well, maybe they are not completely destroying their order, but are they important? And so two questions that we started to answer last week. A is the destruction of the order. B is the not even even if you have the order, are the fluctuations important? So what do I mean by important, and do they destruct the order or not? So this is the coarse grading procedure that we had. Let's assume that this is our system. This is phi. This is x. And the idea of the coarse grading started to develop last week is that, well, if this is phi, or, well, your field, and this is what is expected due to Ginzburg-Landau solution, there is an ordered state. A specific non-zero value, it can be positive or negative, non-zero value of your field. Now, of course, there are fluctuations, right? And those on top of this was our assumption. Right? And the fluctuations are not just anything, they're correlated, so we can approximate them as if they look something like this. Okay? So it's not just a noise jumping up and down, up and down. Due to the correlations, they create structures on top of the solution. This is the assumption. Now, coarse graining procedure is to say, well, you remember how we started to build a field. We had a lattice, or we have a very minimalistic model with a lot of microscopical details. We coarse grain over everything, average over everything, and build a field. So let's do this again, but for the fields themselves. So we can say, well, this is one variable, value of phi. This is another, this is another, this is another, and this is another. Right? What is the sizes over which I have to average? The sizes are described by the correlation length. See? Great. So when I do this, what I obtain, this is the coarse grading. When I do this, I obtain that the fluctuation do affect, and now those values are, well, more constant, but they fluctuate on their own. Okay, so this guy goes to something larger, this is going to something smaller, larger again, 0, larger. So I have some fluctuations over my field, and when I average again, Again, I perform my coarse graining. Now taking this, taking this, and taking this, I smooth all those fluctuations little by little. So each coarse graining procedure smoothens the fluctuations because I average over the disorder, I average over the fluctuations that I have, and eventually the idea is that after a while I will get a single solution which corresponds to my original solution of mean field. Right? Just average over the disorder. Average and average and average and average and average, and eventually you'll get your final solution, which is the Ginsburg-Landau solution. Very, very simple. So this is coarse graining. Right. So our idea over here is to see how those fluctuations behave when we start to coarse grain. Okay? So, are they important or not? Do they destroy the disorder or not? Okay? Is going to be visible when we average over the respective length scales, which are Xi. And that's it. Right? So, to answer the first question, do the fluctuations destroy the order we have due to this procedure? We want to average, and we will see if after averaging procedure, okay, eventually we're getting that the fluctuations destroy the order, yes or no. We will see this. How do we will see this? We expect that after we average for larger and larger length scales, eventually all those fluctuations will disappear and will converge to zero, right? So if I'll describe the variance of the fluctuations, the variability of the fluctuations, I expect that after sufficient averaging, and everybody here who've done anything related to data, you know that you need more data and you average more, and then you get a very nice fitting or a very nice line. And if you have a crappy data or you don't have enough of your data and you try to average, you will see a lot of fluctuations. We call this statistical noise. Okay? The same idea over here. You average and you average and you average. The noise has to disappear. No noise. Convergence to a constant value. Okay? And this your constant value is what? Is the mean field solution. Right? So let's see if indeed this is the case. Questions? No? Right. So what I'm doing here, I'm constructing the fluctuations. Not this. Sorry. I'm constructing a coarse grain description. So I have delta m. Remember, delta mx is the fluctuations, and now I'm constructing delta m hat, which is averaged fluctuations over some specific region. Okay, so this is coarse grain fluctuations. Okay. The region over which I'm going to coarse grain somehow has to be defined by my correlation length. So the region of coarse graining region is V. That's related to C, and it's approximately C to the power D. Right? Assume that I have a cube, which each side of this cube is provided by the correlation length. So, what is this delta M, the coarse grain fluctuations? It's simply delta M hat is 1 over V C, an integration over this volume, V of C of d dx delta mx. Just sum up, so this is the expectation value, the average value. I sum up over all the fluctuations in specific region and I divide by the size of this region. That's it. Okay. All right. So first of all, I know that delta M average is 0. It has to be 0. Why? Well, because it's an average of V C, an integral over V C d dx delta M x average. So an average of an integral is an integral of the average. F1 over V C, an integral over V C d dx, and here I have an average of delta M x. We know that the fluctuations on average do not contribute anything at given specific point, right? So this is simply 0. Great. So yes, on average, fluctuations do not contribute, but this is not what we were asking, right? We want to see if there are fluctuations after I perform averaging, okay? Their variability is giving us something which is not 0. Okay? That's the assumption. Either they completely go away, what is called self-average. I average over many different realizations. I enlarge my V of C, so on average they contribute nothing, but there are some fluctuations about 0. I want to see the variance, okay? The variance of delta M. This is what I want to see. Right? I have a random variable. This is a random variable. Okay? It's average random variable. I know that it's 0 on average, but is it 0 always? My question, or my hope, is that it's always 0, and then the mean field is always correct. Okay? That's the hope. So let's compute the delta M. So first of all, what is delta M? The variance is delta M hat squared average minus delta M hat average squared. We know that the delta M hat is 0. That's what we computed over here. So the variance is just delta M hat squared average. Right? So to answer this question, do they contribute or not, we have to compute the second moment of our coarse-grained fluctuations. So how we compute them? It's actually really simple. So first of all, let's write down what is delta M hat squared. Okay. It is 1 over V C of d dx delta M x, right? Multiplied by 1 over V, and I just do not write the same value x, I write the integration value y, doesn't matter, C, an integration of d dy delta M y vector. Okay. This is what I have. I don't care if I call this integration value x or y, it's all the same. Okay? And over the top of this, I have to perform averaging. Average, average, and average. Okay. Now, that's the same trick. You write this down as a double integral, and double integral is a linear operator, so all the averaging is performed inside the integral. Okay, so it is 1 over V C squared, an integral over d dx, an integral over d dy, and here I have delta M x, delta M y, average. So I have a double integration over a specific function, delta M x, delta M y, okay? And I have 1 over V squared outside. Oh, sorry. Okay, what's the next step? The next step to realize that this part, delta M x, delta M y, right, average, we can write down as delta m x, delta m x plus y minus x average. Okay, and this part down here is what? This is the correlation function g of y minus x. That's it. So we have to integrate, perform a double integration over correlation function, okay? And this correlation function depends on the y minus x. Okay, so I change variables because I can fix x, and for any fixed x, I can modify y. So instead of integrating over an x's and y's, I say that this integral, okay, this integral is 1 over dc squared, an integral over d dx, and here I have dr, right, g of r. That's it. And y minus x is r. So let's write it down as ddr.
Wait, isn't the other one?
So it's the integration goes like this. So you had an integration over y and x, and you have to perform a double integration. So I'm saying let's perform integration in this form. Okay, that's it. Okay, now we can integrate over ddx first. Now remember, in all of those integrals, I will write it down, in all of those integrals, remember we have this, and the integration is always over a specific volume, which is v xi. So this is v xi and v xi, and here it's going to be v xi and v xi, okay? Also here, v xi and v xi. Next step is to realize something. And what I want to realize, so first of all, this first integral is just vxi. This is the first integral. It's very simple, so the integration over d dx over v xi is simply v xi. Very nice, and we can cancel out 1 over the powers over there. So our total integral, delta m hat squared average, goes to 1 over v xi, and integration over v xi of d dr g of r. The last thing is to notice what is this ddr g of r. Somehow we have to compute it. Now I know the different representation of g of r. We solved it by using Ornstein-Zernicki form, and we obtained out of this Ornstein-Zernicki form, we obtained what? We obtained, we obtained by using saddle point approximation, we obtained the form of g of r. Right? But the precise and exact form of g of r is provided in the Fourier space. Right? Remember, what is the g of r in Fourier space? Do you remember?
1 over k squared.
Exactly. So I know that g of r is some integral by itself. It's some integral in Q space. So I want to use this information in order to compute what g of r is. So what do? I do the following. I'm looking of d dr of g of r, and I'm saying this is the limit of q goes to 0 of d dr of minus I q dot r g of r. I have done nothing wrong. This is the integral. I'm looking on this integral. I'm taking the limit of q goes to 0. Well, you can say, Stas, the limit should be exact inside the integral, but forget about this, those mathematicians. For us, we can take the limit out of the integral. So this is exactly what we have over here. But what is this? This is the Fourier transform of g of r. Great. Why is great? Because we know what is the Fourier transform of g of r. Right? So this is exactly lim of q goes to 0 of g of q. Now g of q, as you said, we know the form. This is the Ornstein-Zernicke form. I remind you that g of r equals to k Boltzmann t divided by a constant large K, an integral of d dq divided by 2 pi to the power of d e I q dot r divided by q squared plus c squared minus 2. Minus 2. So this is, if nothing bad happens, this limit over here is simply g tilde of q equals to 0. Okay, so, but what is g of q? G of q out of this is k Boltzmann t divided by large kappa k multiplied by 1 over q squared plus c minus 2. This is what g of q is. So g of 0 tilde q equals 0 equals to k Boltzmann t divided by large k multiplied by 1 over c to the second power. So it is c to the second power. Okay, so the only thing that's important, the prefactors, who cares about the prefactors, right? Why? Because remember, the goal is, it's always the goal here, coarse grain about around larger and larger and larger regions. The regions are defined by C, the correlation length. Now, so what we've got that there is a what is depends on the correlation length, the prefactor or the volume over here, and this guy. Okay. So notice the following. We obtain that delta n hat squared average equals to 1 over vxi. So this is already, we already stated, is 1 over c to the power d. Now, whatever is left, this integral over here is just k Boltzmann t divided by large K multiplied by c to the second power. Okay. So delta m average squared goes like, this is what I told you, forget about the prefactors. The prefactors are not interesting. You enlarge your coarse graining region. What is your coarse graining region? Is just this parameter c. So you have c to the 2 minus d. And we use large C. Basically goes to infinity. So you notice that due to this 2 minus d, this 2 minus d makes huge difference, right? What was our expectation? The expectation was that after self-averaging, coarse graining, after a while, the fluctuations are not important. When they are not important, the variance have to go to 0. You average over the intrinsic noise, the noise disappears after a while. It should disappear. There are systems where it's not happening. And what this tells us? This tells us that for 2 minus d larger than 0, delta n hat squared average diverges. C goes to infinity. So you average, you include more fluctuations and more fluctuations and more fluctuations, and they do not disappear. So something is wrong, right? What can be wrong? What do you think? So remember the question that we tried to ask. We assumed, that there is a homogeneous solution described by the Ginzburg-Landau formalism. There is one single point, one single realization of the field, and there are some fluctuations on top of it. Now we averaged over those fluctuations, and somehow those fluctuations, the averaging, created even more fluctuations, and even more fluctuations, and even more fluctuations, and even more fluctuations. So what it means is that nothing happens. What I mean by nothing happens after averaging means that there is no homogeneous solution. So no mean field solution. For d smaller than 2. The original assumption that, well, you can find a single realization of the field. There are a huge number of realizations. You can find a single one, okay? And the single realization, this is described by the mean field, and the system converges to this one single realization. It's somehow wrong for low dimensions, right? So what happens at low dimensions? You remember the Goldson modes, for example. You always have some symmetries. So what this tells us that there is no one specific realization, one single realization where you're stuck, okay? The system can go from one realization slowly by soft modes, like those Goldson modes, to a nearby realization, to another realization, to another realization, to another realization, to another realization. And you can travel like this. So you're never stuck. The system explores infinitely many different realizations. Those are your fluctuations in the system. And even when you average over them, it's still not converging to anything. So not mean field. This is called, so d equals to 2. It's called the lower critical dimension. Whatever I've told you about the critical phase transition and Ginzburg-Landau superiority, etc., it's nonsense. For low dimensions, it fails. There are no phase transitions, at least for whatever we've been doing, at low dimensions. Why? The fluctuations can always overcome the uniform solution. Now, you have to be careful about d equals 2. We proved it for a specific Ginzburg-Landau, right? You can modify the Ginzburg-Landau. So, for example, for the Ising model, you can show that exactly at d equals 2, you have a phase transition. The next dimension is d equals 1. You don't have a phase transition at all. For one-dimensional Ising model, discrete, you don't have phase transition. For 2, you do have. For 1, you don't. So when you have a discrete system, it's a little bit tricky. What is the lower critical dimension? It's usually very low. D equals 2. Okay, so whatever I've been doing somehow should be okay when 2 minus d is smaller than 0. So okay, so we can live maybe in 2 dimensions, apply this Ginzburg-Landau, or in 3 dimensions. And you know, if you like higher dimensions, maybe you can apply it in 4 dimensions, 6 dimensions, whatever those dimensions are. But this was the first question. So now we know that fluctuations ruin completely mean field representation in low dimensional systems. Absolutely ruin them. Why? Because there are soft modes, and the soft modes can make your system escape from one single realization. Now, in the language of physics, what we obtained is that there is no ergodicity breaking and no spontaneous symmetry breaking in low dimensions. In low dimensional systems. What I mean by ergodicity breaking? If you remember, ergodicity breaking tells us about the equivalence of time averaging, okay, and ensemble averaging. And in this case, it tells you the following. If you imagine your state space or phase space of the system, let's assume that this is your phase space. Landau-Ginzburg's single solution tells you that you're not exploring everything, right? So you have a very specific realization, and the system lives in a small vicinity around this realization. So it means that whatever phase space you have, Ginzburg-Landau tells us you live here. This is your home, and you never escape it. This is ergodicity breaking, because for ergodicity to hold, you have to visit all your phase space somehow. Somehow you have to visit everything, every point in your allowed phase space. Ergodicity breaking tells us, no, there is very small realization, or a set of realizations, your Ginzburg-Landau solution, and some fluctuations around your Ginzburg-Landau solution, where you live. Okay. This is the only, how you obtain it. Remember, we have this saddle point approximation. We had this huge integral, we approximated, and the saddle point approximation, this wonderful technique, it told us, pick one, just one single realization, and this is your solution. On top of this, you have some fluctuations. Okay, so this is your region in your phase space, but actually, your total phase space is much larger. But you never visit the red region. You always hear. This is ergodicity breaking. When your phase space, instead of visiting everywhere, you limit it to a very small region. Okay? Why it's also called spontaneous symmetry breaking? That's related to the Ising model originally. Because all of this, although we treat this as in Ginzburg-Landau, Hamiltonian, etc., but all of this is about Ising spins, right? Spins that are pointing up, spins are pointing down, spins are pointing forward, spins that are pointing backward. Ginzburg-Landau solution tells you that there is one variable realization. there is a very specific direction where the spins prefer to point, right? So I have a phase transition and majority of the spins are pointing over there. Now, why this direction? There is nothing in the interactions between the spins that prefers this direction. I haven't applied any external field, okay? But that's the ergodicity braking. You have a very specific portion of your phase space, and somehow, due to the interactions, you point in this direction. And spontaneously, all the spins are stuck in this specific point on your phase space, and you're pointing in one direction. All the spins are pointing in one direction, and this is a spontaneous symmetry braking. Although you have symmetries, and you can point over here, over there, over here, over there, right? You can point anywhere, but the saddle point approximation tells us you're stuck. And when you're stuck, you're stuck. And if you somehow been pointing in that direction, you're going to continue to point in that direction. So that's it. So those are two phenomena related to each other, and this is what occurs during phase transition. What we've shown is that no ergodicity braking and no spontaneous symmetry braking occurs in low dimensions. Why it does not occur in low dimensions? Because the fluctuations are too hard. Because the system has soft modes, those Gaussian modes, or the creation of the domains, and it does not cost a lot of energy to shift the system from one point to another. So instead of always pointing in one specific direction, well, from time to time, a fluctuation will shift everything a little bit to the left, and then more to the left, and more to the left, and more to the left, and eventually, you start over here, right? You're saying, well, you have small fluctuations. Yeah, you have small fluctuations, and you're wandering around your allowed region. But the fluctuations continue to drag you, so you will eventually get out of this small region, and due to those fluctuations and the symmetries of the system, you will explore all of your phase space. Okay? And there are mathematical theorems how exactly you explore them. That's not really important for us. But the point is that the fluctuations that are always present, thermal fluctuations, okay? I'm not talking about the situation when your temperature is zero. When the temperature is zero, it's a very different thing. When your temperature is finite, no matter how low it is, it's still finite. Eventually, thermal fluctuations will drag you everywhere. Okay? That's what we have shown. This happens for low dimensions. All right, so we understand that we don't want to, or we cannot use the low dimensional physics, but maybe we can do something in 2 dimensions or 3 dimensions or whatever. Question, yes?
I'm a little confused. So the spins don't break ergodicity, but the fluctuations do?
The system. So when you look on the ergodicity property, you look on the whole system. For example, you look on the magnetization. You take an observable. The statement of ergodicity is very clear. It goes like that. You take an observable, in your case, it's the magnetization. And you measure it as a function of time. Okay? Now, your allowed magnetizations span from +1 to -1 in some units, all right? Now, ergodicity braking means the following thing. That you're stuck in a vicinity of very specific state. So this is your M0. You below the critical temperature. You have an ordered state, and your fluctuations, or the expectation is that you're wandering over here. Okay. Now, if you consider the so when you measure what is M, and this is going to be time average, it's 1 over the time, an integral from 0 to t, m as a function of time, dt. This guy fluctuates as a function of time, okay? And when t goes to infinity, okay, it converges to a very specific value, okay? In your case, it will converge to m0. Okay, great. Now, so this is, you say, well, fine, this is indeed a specific solution, and I have m0, very, very nice, and measure is great. But when you consider, so we have ergodicity breaking, tells you, so that m hat equals, in the t goes to infinity limit, to the average m. Okay? To the average m. But what is your average m? So this is time average, this is ensemble average. This is time average. Ergodicity breaking is the equivalence of those two averaging. You can take an experiment or your simulation, whatever you do, you look on your quantity and you register its positions or its values as a function of time, and then you average over all possible recorded realizations. Great? So this is your time average. What is the ensemble average? In ensemble average, when you solve everything theoretically, you obtain that you have one solution, m0, but you have another one, right? Minus m0. You have another solution. And this another solution is over here. And your average m, when you average, so you have exactly the same probability to be at m0, and you have exactly the same probability to be in minus m0. So m average is 1/2 m0 plus 1/2 minus m0. So it equals to 0. Okay? When you do ensemble average, you obtain that the average magnetization is 0. When you do temporal average, you obtain that the average magnetization is m0. m0 does not equals to 0. Okay? Although it can be small, but it does not equals to 0. So ergodicity is broken. And that's also related to spontaneous symmetry breaking. Because the symmetry of the system says you can all point upwards or you can all point downwards for the majority of the system. And it doesn't matter, it's always, it's the same probability, right? It's the same probability. So on average, you don't point anywhere. This is your average magnetization. But when you look on the system as a function of time, it's stuck, right? It's stuck over here. And it's not exploring the whole allowed phase space. That's the whole point of ergodicity breaking. And there are a lot of theorems about how it's allowed to explore the space. Not really interesting for us. Right? So this is what I mean when we do have Ginzburg-Landau solution. Ginzburg-Landau solution picks one specific state. One state. And it says, you see it over there. How? Remember all these integrals and you have this Laplace integration, etc. It picks one single solution and you're stuck over there. That's exactly your ergodicity breaking. Instead of exploring this state and also this state, you're stuck over here. Because what do you expect, what you need to have in order for ergodicity to hold? You need to have this, 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 and so on and so forth. So what we have obtained that for 2 minus d greater than 0, the fluctuations matter, okay? What happens for large systems, instead of seeing the system stuck in one specific state, you will see creations of those domains. Up and down, up and down, up and down, up and down on all scales. This is why the ergodicity is not broken. This is why the spontaneous symmetry is not broken. There is no spontaneous symmetry. Okay? Nothing. Why? Because the fluctuations are too large and they take you from one position to another position, from one position to another position. That's what happens. Okay. All right. Yes.
So it's kind of like the degrees of freedom need space to put the excessive energy in some sense.
No, it's not that they need space. They always have this possibility somehow due to dimensionality to push your system from one side to another. Or maybe you're right. So what do you mean?
Like there's in your interaction, there's some places that you prefer to put the energy.
Okay.
Right? And there are, so the idea is that the degrees of freedom put all the energy there, and then they can order in the other parameter.
Okay, maybe. It's a nice idea. Maybe. But let's stick with the fact. It's hard to exactly explain where the system goes. So we know that there are goals and modes, and those goals and modes push you everywhere, or you have creation of domains. Okay, this is good. Now, do we have anything else? So first of all, we have this lower critical dimension. Yes?
So just to think about it in like in terms of experimental results,
Mm-hmm.
does that mean that, for example, for a 2D material will not show magnetization? Like,
So no. So it depends on the symmetries. So what we've got, it's for a specific form of Ginzburg-Landau field theory, right? This was the phi4.
so
For example, let me finish. If your system is Ising-like, okay, the critical dimension is d equals exactly 2. It's lower than 2, and at 2 dimension you will see magnetization, spontaneous symmetry breaking, everything. You see d equals 2 is on the border, exactly on the border, so you have to check it. Yeah, that's what it means. But you do see magnetizations in numerical systems, in whatever. Now, you remember we had a lot of assumptions. So for example, the interactions were short range. We put a lot of assumptions on the way. So sometimes you can say, oh, I see in one-dimensional system, I see magnetization, I see phase transitions. Whatever Stas has told us is completely not true. Well, maybe, but actually, we had a lot of assumptions on the way. And it's as usual in physics, when something breaks, you have to check your assumptions. So, for example, the interactions, maybe they are long-range interactions, etc., etc., etc. So you have to check your assumptions. But in general, for a low-dimensional system, low enough, it's or 1 or 2, you won't see a phase transition. Yes. Okay. Now, next step. What do we do? Erase something. Erase this. All right. So we know that the fluctuations are less important for dimension 2 and above, or above 2. But when I'm saying less important, but maybe more important, so less important with respect to what? So this criteria tells us that the variance diverges for low enough dimensionality. It means that the variance is actually converging to 0, right? But where it's converging to 0? It's converging to 0, so let's look on this. Delta m squared goes as c to the power 2 minus d. So when we look on d larger than 2, above the critical dimension, lower critical dimension, we know that delta m average squared goes to 0. All right, this is what we wanted. Where? When c goes to infinity, right? You coarse grain more and more and more over larger and larger regions, and eventually you don't care about the noise. But something else happened in this, specifically in this region where c goes to infinity. So where c goes to infinity, how to take c to infinity? Remember, what is c?
Correlation.
Correlation length, and it goes as 1 over square root of T minus Tc, right? So in order to average over larger and larger regions, okay, so for your C to be large, you need to approach the critical temperature, right? Great? Great. What happens when you approach critical temperature? What happened to your order parameter? Is it constant? Is it large? Is it big? Is it small?
Goes to 0.
It goes to 0, right? So your order parameter, M mean field, goes to 0 as C goes to infinity. As simple as that, right? That's it. So great, the correlations or the fluctuations are getting smaller and smaller, but at the same time, the mean field solution is also getting smaller and smaller. So who's important? And then, oh, they're both small, but when they're both small, what's important is the relative size. Okay? So if I had a situation where my mean field was constant, no matter what the temperature is, okay, I average more and more and more and more, the fluctuations go down, I don't care about the fluctuations, I'm only left with what? I'm only left with the mean field solution. Great. But the procedure here is different. I take those regions and I say I want to increase this region and make it larger and larger and larger, approach the criticality. And at the same time, the mean field solution also getting to 0. Okay. So yeah, the fluctuations are small, but the solution is also small. So small is always with respect to what? Okay, so sometimes one is very small and sometimes one is very big. Sometimes 10 to the minus 6 is very small and sometimes it's very, very big. So what we have to do, and what is called the Ginsburg criteria, is to check the relative size. So Rg, this value, is simply delta M, the variance of the averaged fluctuations, divided by the mean field solution to the second order. Okay. You have to take care that the units should be exactly the same. This is why it's to the second power. This is also to the second power. And you check those guys. So what do we know? So first of all, we know the only thing that's important is the dependence on C. And C goes to infinity, so we approach the criticality. We approach this criticality. What do we know about this one? This one goes to the C to the power 2 minus D. So we have C to the power 2 minus D. Great. Okay. What we have in the denominator, we have mean field to the second power. So this one, we showed it before. It is C to the minus 2. Okay. We obtain that this goes as C 4 to the power minus D. Okay. So again, we have something that can either explode or go to 0. It all depends on the value of the D over here, the dimensionality. Okay. So what happens when D is smaller than 4?
The fluctuations win.
The fluctuations win. Okay. Rg goes to infinity when C goes to infinity. Right. So for the dimension D smaller than 4, okay, fluctuations win. What it means? Ginsburg, Landau, mean field fails. for d larger than 4, Rg goes to 0 as c goes to infinity. Mean field wins. That's it. So, what we found, first of all, we found the following. We have a lower critical dimension, d equals 2, below which there is no phase transition whatsoever. Okay, great, so no disorder. Now, the fluctuations are not so important, or they absolutely not important, for d above 4, so d equals 4, hold upper critical dimension. We can say with certainty that whatever be done for almost all any system is that the mean field is the right way always true for d larger than 4. Well, if you have a 4-dimensional system at hand, as experimentalist, for example, you can apply mean field. That's great. But if you have, like normal person, a 3-dimensional system, a 2-dimensional system, so you're out of luck. It's not exactly that you're out of luck, right? But something else. There is something else inside. So those fluctuations, they are important. So something else has to happen inside your system. Okay. So for any d larger than 2, smaller than 4, which is sometimes d equals 2, sometimes d equals 3, you can say, well, I have a fractal system, d equals to 2.7. It's also fine. There are such systems like that. But here, we need to find a better theory. So it's not that the fluctuations ruin everything. So it's not that the mean field is completely useless. It's qualitatively fine. Mean field tells us there is a phase transition. There is a second order phase transition. Something happens at this phase transition, but it probably predicts the phase transition wrong, and it probably predicts something else wrong. So qualitatively, yeah, mean field. Quantitatively, not so good. Right? That's the main problem. So what we'll try to do next is to find this better theory. Now, before this Ginzburg-Landau, and before this exact mean field way of thinking how I describe it to you, based on statistical field theory, people already understood that something peculiar happens. Right? So that you don't need exactly to find this critical, upper critical dimension, lower critical dimension, etc., etc. You don't need to include all those fluctuations. Theoretically, you can go to a lab, you can go to your computer, you can simulate a system that goes through a phase transition, and even there, you can understand that mean field, it's not the way to go. So it, again, qualitatively, okay. Quantitatively, not so good. So what people measured and how people understood that the mean field, it's not so good. We are not going to describe 4-dimensional systems. There was a huge business, 60s, 70s, 80s, to explore different properties in high-dimensional systems because you can do something. When you have, the moment that you have mean field, it's a very practical way to solve something. You eventually have to pick one single realization and that's it. And you're good, you're golden. Right? Either way, well, how to solve it, you don't exactly know. But what people have done is to describe or try to describe or try to approximate different systems using this mean field solution, that we know that it's okay d equals 4. For example, they said, well, maybe in dimension, not 4, but 4 minus 0.1 is going to be fine. And 4 minus 0.1 is almost like 3. So we're going to be fine at 3. There was huge business around it. Not so successful. Sometimes it is. It's a lot of fitting over there. We won't go in this direction at all. So try to build some different understanding of how you build different theory. And this idea that we already used twice in this class, the coarse graining, is going to be very, very crucial and central idea in whatever we're going to do. Now, before going to this coarse graining, once again for the third time, I want to describe to you, we have another 20 minutes, how people knew that mean field is not for us, even before solving everything. And this is the story that was fascinating physicists, 40s, 50s, 60s, 70s, well, basically till ideas of Leo Kadanoff and Ken Wilson arrived. And this is called the critical exponents. For many different systems, people perform the following procedure. First of all, if they have in their system a critical temperature, so they defined a reduced temperature. So it is T minus Tc divided by Tc. This is the reduced temperature.
This was in recitation 1, no?
Sorry?
This was in recitation 1, no?
Yes, exactly. We're going backwards. Now, because I cannot conclude the story about mean field without saying something about critical exponents myself. That's why. So what people measured? So we know that when t goes to 0 minus and h external field. Don't worry, I won't develop everything. I will just state a lot of facts. We know that the magnetization, or people who measure the magnetizations or any other order parameter, it was as minus or absolute value of t to the power of beta. Okay, magnetic there was magnetic susceptibility. Good that you remember what was in recitation 1. Probably you did your homework for the quiz. He is dm to dh. H goes to 0. And it was t to the power minus gamma. And there was correlation length that people measured. Correlation length. And this scaled as t to the power minus n. They used almost all the letters in the Greek alphabet. There was heat capacity, and the C, and it scales as t to the power minus alpha. And at T equals to Tc, exactly at the critical temperature, they know that M scales as h to the power 1 over delta. Now, there's a lot of historical reasons why it's alpha, why it's beta, why it's 1 over delta, not just specifically delta. We don't care because, well, it's history. You can open a history book on science and read all of that. I'm trying to make a different point. And even people measured the correlation function. So correlation function everything was measured in the vicinity of the phase transition. Okay, G of R is 1 over R d minus 2 minus eta at t equals to 0, and R goes to infinity. I think I'm done with all the different letters. So what we have alpha, beta, gamma, delta, ni, eta. And probably there are more critical exponents. And what fascinated people is that you can take this material, measure all of those exponents, okay, and then go to completely different, but looks that completely different material, but it has a phase transition, go into the vicinity of this phase transition and measure exactly the same exponents. And then make a third, or somehow find a third material, go to the critical point where you have a phase transition and measure exactly the same exponents. So those alpha, beta, gamma, delta, ni, eta, universal. Now, universal, it's not that there is a single set of alpha, beta, gamma, delta, ni, eta, okay? They're classes. It depends on the symmetries of the system. People found it depends on the dimensionality of the system, but there were classes of those exponents, okay? And this, for a physicist, when you see exactly the same behavior, although the microscopical constituents are completely different, okay? This is like a huge light saying, interesting physics, interesting physics, interesting physics, right? So, and people knew about those exponents from the 40s, 50s, 60s, 70s, okay? And this is what stimulated the Ginzburg-Landau formalism, the mean field approach, etc., 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 is the existence of those alpha, beta, gamma, delta, ni, eta, and people have talked about universality classes. Okay. Universality classes. Basically, the idea is there is something intrinsic about the system that depends on the symmetry, on the dimensionality, near the critical point. It only holds near the critical point. So somehow when those fluctuations come inside the interactions, they fluctuate over the whole system, somehow the physics become universal, right? It's like the law of gravitation applies over here, and over there, and over there, and there, and there. It applies everywhere, right? Universal law. So somehow, near the criticality, there are some universal laws that completely don't care about the microscopics. They care about some other things, and they define those alpha, beta, gamma, delta, ni, eta. Okay? Those are the critical exponents. And this is why it was interesting. This is why people focused on phase transitions, some new interesting physics, and they describe different classes, universality classes, etc., etc. Now, what mean field tells us? Mean field, when it was developed, originally for the Ising model, but then more generally like the Ginzburg-Landau, and you have different Ginzburg-Landau theories you can apply to different materials. You can say, well, my order parameter is not scalar, it can be a vector, it can be a tensor. You've seen a lot of examples so far, and how to solve them, etc., etc. But when you do the mean field, okay, you usually get stuff like gamma mean field equals 1, delta mean field equals 3, alpha mean field equals 0, ni mean field equals 1/2, eta mean field equals 0. So you see that the numbers are a little bit boring. They are, either they're even not a real number. They're rational numbers, okay? And people knew from simulations, from experimental data, they knew that there, for example, exists an Ising class, three-dimensional Ising-like model that's applicable to ferromagnets, huge number of uniaxial ferromagnets, binary fluids, lattice gas, liquid gases, all in the class of Ising-like 3D systems, the microscopical description can be completely different. Okay, but internal symmetry somehow make them similar. For those guys, the beta was 0.3668 something. They invest huge number of time of computing all those numbers. You couldn't even believe how much time. Gamma is 1.24. Mi is 0.63. People know what the different numbers over here. And it never stops, it's something. Eta 0.036. I never believed this number, which is 0.036, but they're sure that this is the number. Okay. This is very different from what the mean field describes to us. And the mean field, it's independent of the dimensionality. We know that we take an Ising model, we bring it in 2 dimension, those numbers are going to be different, okay? And it's going to be a different universality class that describes 2-dimensional systems. So this where people knew, even without all those fluctuations, etc., 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 people knew that something is broken. Something intrinsically broken inside the system. So we know that there is very interesting universal physics there. Okay, we try to penetrate and understand what the physics is by using this ergodicity breaking idea. We said we have only one realization that's important. That's what the claim was. One single realization was important, and this approach fails. Not always fails, right? It succeeds in dimension 4 and up, okay? But you don't care about the 4-dimensional systems, neither do I. So something interesting is inside. People knew that something interesting inside, and they tried to understand it. So huge number of experiments, numerical simulations, connections between all those different alpha, beta, gamma, delta, and mi, eta. Okay, so there are connections between, they are not exactly completely free exponents. But for us, we don't care about them. We only care about the following fact. There are universality classes. Those exponents tell us that there are universality classes. And there is an interesting physics that we have to find. And we already know, by dealing with this Ginzburg-Landau approach, that somehow fluctuations are inside and they become much more important, in some sense, than the mean field solution. So it's not that the mean field solution completely fails, it's that you cannot simply say there is one single realization. The system is not exactly stuck in some solution. So what is the usual approach and where it's exactly failed, right? Yes. Let me be a little bit formal. Where we failed. So what were the approximations? Approximations were we had a field. So the first approximation, you perform coarse graining, and in this coarse graining, you build up a field. Out of this field, you constructed Hamiltonian, which was a functional of the field, and it was some sort of an integral, okay, over a function f of phi x dx. Okay. First, you coarse grain. Then you assume that you can construct a Hamiltonian. In the Hamiltonian, you said you have a specific density which is local after your coarse graining. And you have to average over this in order to get this field. And in order to obtain the Hamiltonian, you have to sum over all the different realizations on the field inside. Okay, this was an assumption. Okay. Next, after you have this Hamiltonian, in order to compute something, you need the free energy. In order to get this free energy, you need the partition function. Okay. And this partition function, you have to sum up over all the possible realization of the field. Right? It's not that you take one field, oh, it's great. You have, and we explained it, you have to perform a functional integration over all possible realizations of the field in all different x's, okay, of the function e to the power e to the minus beta the functional of phi. Okay. So a lot of assumptions. This, that, this. Okay. But where we failed, where the point where we said we start with a hammer and said this is the Ginzburg-Landau approach, okay, and this is the solution of mean field. When we have taking all of this integral, was the weakest point. We have taken this and we said it is e to the power minus b of h of some specific phi 0. You have taken one realization of infinitely many realizations of your system, and you said this is the one. Okay. This is the symmetry breaking, this is the ergodicity breaking, this is all those breakings. You pick something and you said you sit there, you choose it, and you never set your foot out of it. Okay. So something somehow happened over here. Good. And the mean field fails, and what we have to question is this transition. So we know it's failing in D between 2 and 4 somehow. It's fine somehow again for D larger than 4, right? So what we are going to do is to try a little bit different approach than what we've done over here. And this approach is called a renormalization group, and it's based on the ideas of coarse graining. So before I do the formalistic renormalization group, I will try to describe to you those ideas of renormalization, not on the fields, but on much simpler system like random walks and sums of random variables. We are going to do this after Hanukkah. So happy Hanukkah for you all, whatever you're celebrating. And good luck with the quiz. That's it for today.
Thank you. Thank you.
סיימתי את כל מה שרציתי. היה עוד אחד, היה קפלינג, צריך להסביר על קפלינג, אבל בסדר, לא...
רציתי לשאול על אחד הארגולוגיות שאנחנו עושים ממוצע בזמן. כן. גם בדיוק אנחנו מתכוונים לממוצע בזמן לשדה שלא תלוי בזמן.
אבל יש לך פלוקטואציות טרמיות, אז אתה עוקב אחרי מגנטיזציה. אתה לא עושה ממוצע על הפי, נכון? אתה מסתכל על האורדר פרמטר שלך, ואתה מסתכל על כולו, נגיד אתה עושה אינטגרציה של מסכם על כל הספינים, ואתה מסתכל על זה כפונקציה של זמן. ואז הוא לא זז. לא זז נהדר, יש לו m פלוס אפסילון, n מינוס מאפסילון. זה האינטגרציה שלך. השדה שלך הוא קבוע בזמן, בשביל הפתרון הספציפי הזה, הוא יכול להיות טיפה להשתנות. אבל לא תמיד קבוע, נכון? הוא משתנה מנקודה לנקודה.
אז אולי הדרך הנכונה, אולי זה לא דרך נכונה לחשוב על זה, אבל נגיד בממוצע של מסלולים, כמו כזה עץ ברנולי, ואז יש מסלולים שהסתברות פי בגלל הטמפרטורה הוא יתהפך, והסתברות פי הוא לא יתהפך או משהו כזה, ואז יש לי מלא 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 מסלולים ועליהם אני צריך למצא.
אתה בעצם אומר, כן. זה בדיוק זה.
זה.
אני אומר, תסתכל, הממוצע בזמן, אתה אומר, אני יכול לעשות ככה וככה 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 וככה, ויש לי את כולם, ואני צריך לקחת בחשבון את כל הדברים האלה, נכון? נכון. שבירה של ארגודיות אומרת, אתה יכולת להגיע לכל המקומות האלה, נכון?
כן.
אבל, אתה בחרת רק את זה. את זה בחרת.
נכון.
זה שבירה של ארגודיות. אתה נתקעת באיזשהו מצב ולא זזת ממנו, למרות שיש לך עוד מצבים אפשריים. זה מתרחש כיוון שספציפית המעבר לעבור ממגנטיזציה א' למגנטיזציה ב' עולה יותר מדי אנרגיה, לכן אתה לא עושה את זה, לכן אתה תקוע. כן? יש לך איזשהו מחסום פוטנציאל אדיר, כן? שהמערכת שלך לא מצליחה לעבור באיזשהו זמן, בסקלת זמן נורמלית. כן? אז אתה תקוע, אז כמו שפה אתה תקוע, אתה לא דוגם את כל המסלולים האפשריים שלך, אתה חי על מסלול אחד בלבד.
אוקיי, סבבה.
ואם אתה עוד רוצה לנפור בזה, אז זה נקרא שבירה חזקה של ארגודיות. יש משהו שנקרא שבירה חלשה של ארגודיות, ועל זה אני ואלי עושים מלא מאמרים. זה הדוקטורט שלי על שבירה חלשה של ארגודיות.
במערכת אבל שהיא כן ארגודית, אז אני בעצם אומר שכאילו...
אתה יכול לקחת את כל מסלול, בסוף הוא דוגם את כל מרחב הפאזה.
אוקיי, כן, כל מסלול יש הסתברות מסוימת.
נכון, ואז אתה אומר, לא, ניקח את זה בחשבון, ניקח את זה בחשבון, ניקח את זה בחשבון, ולכל אחד יש את המשקל שלו, וזהו.
וזה אמור להיות שווה לממוצע שלנו.
נכון, נכון. זה הנחה, במכניקה סטטיסטית רגילה, נניח בתואר ראשון, אני באיזשהו שלב אני מספר לכם. אנחנו מניחים הנחה של ארגודיות. יש חומרים ששם הארגודיות לא מתקיימת, אוקיי? אנחנו לא נטפל כרגע בחומרים האלה. אבל היא שם, ברגע שאתה עושה את המעבר פאזה, אתה שברת ארגודיות.
בסדר. תודה.
טוב,
זהו, אוקיי.
רציתי להגיד לך שכאילו כשראיתי את הבוחן של סטטיסטית וראיתי זה לנדאו, חשבתי אוי.
שהתבלבלתי והבאתי לך את הבוחן שלכם?
כן.
לא, זה מה שסיפרתי לך. אני הייתי צריך לכתוב 3 בחנים.
כן, כן.
אז הייתי מאוד יצירתי בבוחן הראשון. כתבתי על י"ט בכסלו, כן, הייתי מאוד יצירתי, כן. אבל אחר כך היצירתיות שלי ירדה, ואז חשבתי על פחות או יותר רעיונות לא יותר מדי רחוקים, אז לכן הם קיבלו גינסבורג לנדאו. בסדר, זה לא, כן, כן, הבנתי. אם הייתי רושם שם גם פי באיזושהי חזקה, הם בכלל היו...
כן.
כן, אליהו.
שאלה קטנה לגבי D. אמרנו שמתי שבעצם D קטן יותר מ2, אז אין לנו...
בגינסבורג לנדאו שאנחנו...
כן, כן, כן. בגינסבורג לנדאו אנחנו רואים ש-D קטן מ2, אז יש לנו איזושהי סיגמה. סיגמה. השונות שלנו בעצם מתבדרת, אין לנו מעבר פאזה, אין לנו... אז השאלה שלי היא, האם אפשר לקשר את זה לרשתות חסרות סקאלה? כי גם בהן, ברשתות חסרות סקאלה, יש לי את המקדם גמא שלי, וגם בו עם גמא קטן בין 2 ל-3, קטן מ-3 דווקא, גם כן השונות שלי גם כן מתבדלת לאינסוף, וגם שם אין לי מעבר פאזה בגלל זה.
אותו סיבה, הסיפור של מעברי פאזה, ואני שמעתי את הקורס רעיונות על דברים כאלה, גם על רשתות משלומו, והוא יש לשאול אותם, מבין בזה אני בטוח הרבה יותר ממני, אותם סיפורים.
זאת אומרת, זה כן יש איזשהו קשר עמוק.
אותו סיפור, רק שאתה צריך לבנות את מה שאנחנו בנינו, לא בצורה רציפה, לא עם גינסבורג לנדאו, אבל דומה. אם אתה תמצע את כל הרשת זה אותו סיפור.
זה לא סתם מרגיש.
לא, 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 לא. זה אותה פיזיקה בול. אותה פיזיקה בול, המינפילד שם אולי יתארו אותו במילים טיפה אחרות, אבל זה בדיוק אותו רעיון.
ובגלל זה בעצם כל כי אם אתה מדבר פה על איך קוראים לזה? נו, האקספוננטים הקריטיים, ברשתות זה באמת האקספוננטים הקריטיים שלנו.
כן, כי אתה במימד גבוה חי.
זאת אומרת, כן,
לכן זה עובד. לכן זה עובד, מימדיות גבוהה, המינפילד מעולה.
כי זה ממש הזה, שבטא שווה לחצי.
כן, 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 ויש לך קשרים ביניהם, כן, כן, כן. בגלל שאתה חי במימדיות גבוהה, אמרת לך במימדיות גבוהה. לכן אותי פחות מעניין המימדיות, אבל אותך ברשתות זה לחם חוקך, כן.
זאת אומרת, בגלל שרשתות בעצם הם בממדים גבוהים, אנחנו אומרים זה מינפילד, ובגלל זה כל האקספוננטים הקריטיים שלי ככה, הבנתי. אז יש לי מעבר פאזה בעצם ממש כמו מינפילד.
מה? מימדיות אפקטיבית.
כן, ברור,
כן, כי אתה שם את זה,
אני שם את זה על זה, אז זה יהיה לי בעצם דו-ממדי, אבל יש לי ממדיות.
כן.
הבנתי. בסדר, תודה רבה.
בבקשה.
בסדר. הוא בוחן ב6, נכון?
כן. למדת?
עד עכשיו. טוב, היה הרצאה בלי הרבה אנשים.
מה?
לא היו פה הרבה אנשים בהרצאה?
היו
עובד שוב.
No.
אפשר לשבת אחד ליד השני, זה משהו אחר. מה לא? I'm joking. I'm asking.
And you need to canvas it, right? You want to ask you whether you need to canvas it one by one or okay, let's starting the machine. You have some language tests, right? Language tests.
Me?
Three languages. It's a good master of studying language.
She knows four. How much do you know?
Right.
She knows four. English, Hebrew, Turkish, and Arabic. But Arabic she doesn't really know.
You can study Chinese. I just search Chinese test.
How shall I call it?
You want it? You want to
It's supposed to be called.
really good.
Yeah. Did you like sweet stuff?
Yes. You test this one? I like sweet. That's why I have big.
What's that? נשים לך במים. Ouch.
You're back.
She killed my love.
He almost died. תיזהר, אני אחרים עליך הכניסה את הרשת.
באמת יש לך עוד משהו.
אולי תפתור לי את המוח. אני אעתיק. אחרת אני
תפתרי יותר טוב ממני.
לא פותחת.
עזוב אותי. זה נוח לעבוד.
רציתי. לפחות זה.
אני רוצה לעשות פייתון בטונים חם.
יש לך עוד לא חם. אמרת לזה?
לא, מתחיל.
Is there some bigger button?
Bigger?
Bigger one will be cheaper. If one can buy a lot, it will be cheaper. Is there a box? One box of it?
No. Not in this one.
Shit.
It used to be like 7 shillings.
Yeah.
Now it's 11.
What?
Crazy.
10.9.
כמה בראשת?
Maybe it's cheaper.
In China, food is cheap.
2 shekels.
Shekel is the average price for beef.
The supermarkets in the campus is don't cheat. There are some other places that you can do shopping.
You went shopping in Villa, right? Yes.
Every Thursday.
Only Thursday.
Yeah, they drive me. But this car has some problem. This car, the battery.
Oh.
Yes, her car. It's broken, but they didn't fix it. And also you can't lock it. If you lock it, sometimes you can't unlock it.
Nice.
Yes. And last it took me the first time I go with her to the supermarket and I will back this car. First time I lock it and then I back unlock it with around 5 minutes, 10 minutes, and suddenly it's happened. So
You can buy her car. It'll be cheap.
So what? Which is problem? Progress.
דוקטור. יחס כמו הילדים שלנו. אחד שיעי ופסח. Just in others.
You don't know.
It's not the name of the school. It's others. That came.
You also bet on something. Your home is near all your neighbors. And you have to your home.
I lived in the Netherlands for 5 years, so
Okay.
A and B.
You.
No, 5 years. I lived the place with you. Lived. But that's a bit fun.
Stop. That's enough.
What's the meaning of English? I didn't understand what he asked.
You can ask him. You don't understand something.
But he also used English. Explain to me how it if you can use Chinese, you can stop.
Maybe we'll translate for you to Chinese.
Hi Karin, מה העניינים? טוב.
בשערי הבית לא היו מספרים.
כן, זו הבעיה קבועה. אם זה אותו שאלות, מה יש לשנות?
בנושאי מחשבון. לא, אבל ממה שהוא אמר, הוא היה יצירתי בבוחן הזה. כן, הוא אמר שהיה צריך לכתוב 3 בוחנים להיום. הבוחן הראשון היה, כי הוא מלמד סטטיסטית מתקדמת, סטטיסטית והסתברות וסטטיסטיקה. אז לשלושתם יש היום בוחן. אז הוא היה צריך לעשות 3 מבחנים, הוא אמר, הסטטיסטית מתקדמת הייתי מאוד מקורי.
מאוד מקורי, כמו אמר לי שהוא היה עצלן.
אז הוא היה עצלן בשני הבחנים האחרים. בשני הבחנים האחרים הוא אמר, אז פשוט כבר לקחתי את אותם רעיונות שהשתמשתי בהם בסטטיסטית מתקדמת, וכתבתי איתם את הבחנים. ככה הוא אמר, ככה אני הבנתי. לא טוב ליהודים. אבל בסדר.
אתה זוכר את הקוד של ה...
3232. כוכבית 3232, טלפון. אבל יכול להיות שאני מתבלבל והוא משתמש שבוחן אחר הוא היה בו זה, אז לא.
הוא אמר שהוא כתב
את סטטיסטית מתקדמת? אז אולי אני מתבלבל. והבנתי אותו לא נכון.
לא,
לא ראיתי ציונים גבוהים, אני מבקש. דיברנו על
in the flag. I understand.
האם הוא אמר כמה שאלות צריך להיות? כמה שאלות? זה לא יכול להיות ארוך מתרבות. יש לכם עוד שנה. יש לכם שנה.
זה לא עושים ברגע אחרון.
כן, יש כאלה. אצלנו יש לנו סמיכי כזה.
סמיכי זה חמור.
שורפת לכל מקום. תת לכל שלי. תחזיק סמכות כל שלי. עושה לו טוב. שנה. אתמול.
הוא היה פה, הוא היה מגיע.
Some problem. Are you also have lost the sign for? Okay. So you need to.
כאילו נכנס להרצאות, לא נכנס להרצאות. סתם רוצה לראות את הדברים. סתם רוצה לראות את הדברים.
גם נגיד הוא מחליף את הלוח.
אני מעביר את זה.
עכשיו אם סתם מכניסים אותנו במאחז שאנחנו מחכים שזה כבר יתחיל.
תואר ראשון למדתם שעכשיו.
אני לא מבין איך זה... איך
זה יהיה אצל נשים. כן,
ויש את זה שזה... כמה צעדים ככה לאור הקצה?
70. אתה יודע מה זה בין אדם קשקש? כל שנה הוא גדל. אני חייבת לסדר את עצמי כזה.
אתה מסודר, עכשיו נייד.
לא, אנחנו עדיין. 70 סיימו.
באמת?
כאילו היינו יותר מזה למה לא להתקדם את זה?
אנחנו כשאני רשמתי היינו 30. עשינו מסתרם של 5. אפשר 15 כמות.
במתמטיקה.
He will give us some papers or not?
Probably.
שני החבר'ה שהרוב,
למה את לא יודע? הולך אותך.
באיזה זכות יש לך?
אז ירון, אני פורשת מתגייסה בשבועיים.
וואי.
מתגייסה בשבועיים. משהו טוב. כאילו ישר מאוד.
היית עדיין, הוא לא יכול להיות כזה.
כן, טוב.
לא יודע כי יש שם.
הבאות. אני אחלק אותם כאן. כזה. תעבירו כזה.
Here. יש
אני פה. מה? יש פה מה?
אנגלית.
אנגלית? במחברת? יש. Does anyone else need מה? אתה רוצה לכתוב באנגלית? כן, אין בעיה. מחברת. זה רק מחברת. אני עוד רגע מחלקת את הטופס, הוא גם...
אין כאן מספר.
לא, זה סתם אחרת שייך לברכות.
You don't have to write that.
Describe the name here. Okay. And your... Yes. Okay.
אתה צריך מחברת?
Yes.
מחברת? אוקיי.
You're welcome.
Okay, now I'm handing the quiz. It has one side in English and one in Hebrew, okay? So you can use whatever you prefer.
אפשר להתחיל? אפשר להתחיל?
Here you can write down the answers. The quiz is
עכשיו. 25.
25 שנים.
למה?
טוב, כבר לא שם.
משהו?
16 לחודש.
שבע?
לא, זה 7, אני שם לא. כל מי שאין לו הארכת זמן יש עוד 5 דקות. 5 דקות. 5 minutes for whoever who doesn't have the time, extra time.
סליחה. זה לא כתבתי על זה.
משהו עוד ראשון פה?
We can keep the difference?
Yeah, yes. So wait, I didn't realize it.
Can I do
You want a
yeah.
yeah.
יכול לשמור את זה.
We have 5 more minutes. write your name and the ID. Wherever you want.
Okay.
Yeah, you check in.